Hello everyone, today we are going to discuss a problem named divine tree which is 1400 rated on Codeforces. So let's begin. So there is a tree with n nodes and there is something called divineness of a tree which is represented as d of v. So what you have to do is you have to find the sum of divineness of all the nodes in the tree. So let's first understand what divineness means. So divineness is actually defined as for a node, if you're considering this node as v, so divineness of v would be defined as the shortest value on this path, which is the path from root node to the node v. The shortest path from root node to the node v. On this path, the shortest value of a node is defined as the divinity of a node. For example, on this path, the divinity of the divineness of this node here on this path is d equals to 3, because the shortest node on this path is 3. For example, if you consider this one, so the shortest node on this path is 1, so d of this 1 would be equal to 1. And if you consider this one, then this path you would consider, so the shortest value of the node on this path is actually this one, so divineness of 2 equals to 1. So I hope you have understand this one. So let's move on. So one thing we have to notice that we could actually manipulate the divineness of a node according to our value, but up to what extent means that we could assign a value to a node, we could assign a divineness to a node, but what all values could be assigned to a node. So let's take an example. First of all, we need to understand that either we could make multiple branch trees like this one, or we could make a single branch tree. So just to prove that why this works, like if you make a single branch tree or multiple branch trees, it is the same, like it doesn't change your answer. So what I'm actually saying is that if you make a multiple branch tree or a single branch tree, the possible values of divineness would not change. Like if you consider this one right here, and all the possible values of sum of divinities that could be made with multiple branch trees could be made with a single branch tree. So after proving this, I will move on to the solution. So let's take an example. For example, this is the root node. So for the root node, the divinity of the node will be equal to the value of the node. And for example, there are two values connected to this node. So the divinity of this node is 2, and the value connected to this node directly would be either greater than 2 or smaller than 2, which is the divineness of this node. So if the value of a node connected to this node is smaller, so if the value of a node is smaller than the divineness of this node, then the divineness would change to the smaller value, or else the divineness would remain same as the parent node. So like we have understood that if the divineness of a tree is some value, like for example here it is 2, so when you connect more nodes to this one, then the value of these nodes could be either smaller or greater than the divinity, like the divineness of this node. So if the value of the divineness, like if the value of the node is greater than the divineness of this parent node, then the divineness of the parent node would be copied here. Or else if the value is smaller, for example 1, so the divineness would change to the smaller value. And further, if you make more nodes, then the divineness would remain the same unless an even shorter number, for example 0, is found. Like I'm only considering this example, 0 can't exist here. Yeah, so let's move on. So you have to reconstruct this tree into this tree so that the divineness or the sum of divineness doesn't change. So we'll make sure that the divineness of each node remains the same when we are converting this into this. So what we have to do now is we have to fit all these numbers in a single line. So first we draw the root node, and the divineness of this node is 2, and we know the fact that if the number like the divineness of all the numbers connected to this node would be equal to this node unless and until we encounter a smaller number. So we know that the only smaller number than this is only 1. So at the node 1, the divineness would change. So before 1, we have to place all the numbers that whose divineness we want to be 2. So those are 3 and 4. So at the last we place the node 1, and for these two nodes divineness will be 2, and for the last node the divineness would change and it would be 1. So I hope you have understood this, and 3 and 4 we could place in any order, it doesn't matter, because these are both greater than the divineness of the parent node, which is 2. So after we have understood the fact that all the multiple branched nodes could be converted into a single branch node, then let's continue with the concept further. So what were we discussing? That we could actually manipulate the divineness of each node, but what could be the values that we could manipulate the divineness of a node 2? So let's consider this node, like no, first let's consider, wait, let's consider this node, third one. So what could be the possible values of divineness of this node? So the divineness of this node could vary anywhere between 1 to 2. 1 to 3. Divineness of this node could vary between 1 to 3. And why is that so? Because if this node contains a smaller value, any smaller value than this, then the divineness of this node could be the smallest value ahead of this. So for example, if only 1 is ahead of this, so the divineness of this node 3 would be 1. Like So like if like any number smaller than this, whether it is 2, whether it is 1, any number smaller than this is ahead of this, then the smallest value which is ahead of this would be the divideness of this tree, of this node. So let's consider all the cases where the possible values of the divideness are 1, 2 and 3 for this node. So in the first case, when the you can see the possible value of divideness is 1, which is when the first root node is ahead of this. And when could it be 2? In this case. So here the divideness of this node is equal to 2, because only 2 is the smallest number ahead of it, and if like no number is ahead of this which is smaller than this, in this case, so the divideness would be equal to 3. So I've shown you all the cases where the divideness equals to 1 or 2 or 3. So as we have proved the fact that the divideness could vary from 1 to any number which is equal to this, the value of the node. So from 1 to mod of v is this one, this node, the value could vary from 1 to the value of this node, current node. So now we know that if we have 4 nodes, the value of the first node could be 1, the value of the second node could be anywhere between 1 to 2, the value of the third node could be anywhere between 1 to 3, and the fourth node could be anywhere between 1 to 4. So we know it for a fact. Now we could easily predict what are the minimum and maximum values of the sum of divideness that we could make. So the minimum value would be when all of these numbers are 1, and the maximum value would be when all of these nodes would have their maximum divideness. In the case of 1 it is 1, in the case of 2 it is 2, in the case of 3 the maximum divideness is 3, and in the case of 4 the maximum divideness is 4. And also I am telling you the case in which the maximum divideness could be achieved. So this one is the case for the maximum divideness. So as you could see, the divideness of 4 would be 4, the divideness of 3 would be 3, and the divideness of 2 would be 2, and 1 would be 1. So the maximum divideness would be n into n plus 1 by 2, and the minimum divideness could be the number of nodes, that is equals to n. So I have written the maximum and minimum divideness here, and as per the question we have to make the divideness equals to m. So if m lies in this range, then it is possible to make that divideness, otherwise it's not. So now what I've done is I've written all the nodes and the possible values of all the nodes, and we want to fill here the divideness that we want for each node. So we, as we have proved that we could manipulate the divideness of each node in this range, so we could fill any values here from 1 to 4, here from 1 to 3, here from 1 to 2, here from 1 to 1. and we want the sum of divideness to be equal to m. So what I'm going to do is, since we know that the minimum value of this is always 1, so I will assume that we have to make the sum equals to m minus 4, and I've decreased each of the range by 1. So as we can see, the minimum divideness is equal to 4 and the maximum divideness equals to 10 as per this case of n equals to 4. So our m could lie anywhere between 4 to 10. And let me tell you one thing, that we are not actually considering the place of this node right now. We are just considering what value should we manipulate this each of this node to achieve the sum. So let's consider this example where m equals to 6. So m minus 4 would be equals to 2. So we have to create a sum of 2 using these nodes. So the value of the first node would be 0 anyways, and the value of this one would be 1, the value of this one would be 1. Now that we have achieved a sum of 2, the value of this one would be 0. So now that we have filled every number here, what would have been the actual divideness of these nodes? Now we'll fill this one. So the divideness would have been 1 over here, because this one is 0. So, and the divideness here would be 2, because this one is 1. So like this is this one plus 1 is equal to this one, because earlier we had subtracted 1 from this one. So this one would be 2, this one would be 1. So now let's first see how would you implement this part in the code. So you will run iterate from I equals to 1 to n, which are these nodes. So you will iterate over these nodes and fill the maximum value in this range that is possible. For example, you are iterating from I equals to 1 to n. Now what you would do is, so this range is 0 to I minus 1, right? Look at it carefully for everyone. This is 0 to I minus 1. Now what you would do is, you have to add the maximum number in this range which is less than or equal to the value of m, and that then subtract this value from m. For example, let's consider this value to be c equals to max of I minus 1 comma m, and then you would do m minus equals to c. So what this does is actually, okay, I should have written it with proper ink. It will go away now. So this m actually here is m minus 4, which is this value. So let's do a dry run. For I equals to 1, the value of c would be max of I minus 1, which is equals to 0, comma m, which is equals to 2. So it would be equals to 0, m minus equals to 0, which would be equal to m. So m would remain 2. For the second iteration, the value of I would be equal to 2, and this I minus 1 would be equal to 1, and m would be equal to 2. So actually here it should be min instead of max. Yeah, so for I equals to 2, this would be equals to I minus 1 would be equal to 1, and this would be equals to 2. So the min would be equal to 1, 2 minus equals to 1, matlab m equals to 2 minus 1, because c equals to 1 and m initially equals to 2. So the value of our m would be equals to 1 till here, then I equals to 3, I minus 1 equals to 2, and m equals to 1. What would be the minimum? This will be the minimum. So we would fill C here. Oh, I forgot one step. So let's like it's understood, we are filling C over here, right? So we are filling the value of C over here, and then we are subtracting C from M. So I think this is enough for this part. Now let's see how would be able to implement this, like how, in which order we should set our elements in order to achieve these divineness for each node. So earlier we had seen that if the divineness of a root node is 3, then for example this is the root node. If the divineness of the root node is 3, so divineness equals to 3, then the divineness of its children would be less than or equals to this. If the number is greater than the divineness, then the divineness is equal to the node of the parent. Like for example, if there is 4, then the divineness would be equals to 3, which is the parent, or else if the number is less than the divineness, for example 2, then the divineness would change. So divineness could be actually in decreasing order. So to implement this, we would sort the divineness in the decreasing order. So assume it to be a vector of pair. For example, in this direction is a vector, in this direction it is a pair. These are pairs, and this is a vector of pair. So this is, for example, this is vec. So this is vec of 0, vec of 1, vec of 2, vec of 3, and this is vec of 0 dot first, and this is vec of 0 dot second. So we'll be rearranging in the like if we apply sort, it sorts on the basis of the first pair, first value of the pair. So we want the decreasing order, so we'll sort in vec dot begin, vec dot end, and we will use greater int. So if you like write comma after vec dot begin and vec dot end, and you write greater int, wait, if you write greater int in these brackets, in these signs, and then this bracket. If you write this, then it will be arranged in descending order. Okay, I hope my writing is not that bad. So it will be arranged in the decreasing order of the first value of pairs. So what would it become? It would become 2, 2, 1 and 1. So for so these are the value of divineness of the tree. So the divineness should be always in decreasing order. Now that we have understood the order of divineness, so we should so what would you do if two nodes would have the same vertices? Which node should come first? Like for example, these both have divineness equals to 2. So which node should come first, 2 or 3? Actually the order only earlier I had said that the order doesn't matter. It doesn't matter for the nodes after, like for example, I'm taking this example that like let's assume the first node is 2, then 3, then 4, and the divineness of for example, assume it for a second that these divineness were 2. We need the divineness to be 2 for all 3 numbers, and this should be the tree. So divineness of this would be 2, divineness of this would be 2, divineness of this would be 2. So the order of the nodes doesn't matter, in the sense that if this was 4, if this was 3, then also divineness was 2, divineness was 2, since this node is equals to divineness with 2. So in this, the order of these two didn't matter, because the node which is giving them this divineness is 2, but 2 should come first, 2 should come before these nodes. The node 2 should come before these nodes. So we could actually use this one, that whichever node is shorter should come first. This would serve our purpose. So we would actually sort the vector of pair in this way, that the shorter node should come first and the node with greater divineness should come first. So this was node 2, 2 and then 3, then 1 and then 4. So like if you had to arrange it first of all, let's understand what would be our tree. What would our tree look like? So our tree would look like this: 3, 1, 4. So the divineness equals to 2, divineness equals to 2, divineness equals to 1, divineness equals to 1. So our tree would look like this. Where this one is our root node. Okay. So in order to implement this, you could define a comparator function. So in this comparator function, you would be taking two values, two pairs, pair int comma int. I hope you understand. you would take two pairs A and B. So in comparator function, this one is the first value, this one is the second value. Like this would be A, this would be B, or this would be A, this would be B, somewhat like this. The later values are the values given to B. So we would apply this condition if A dot first is greater than B dot first return true, else if A dot first equals to B dot first, then what would we do? We should check the second value of the pair, and if the second value of pair of A is less than pair of B, return true. So if A dot second is less than A dot first, return B dot second if return true. In all other cases it would return false. So this would be our comparator function. Now we have to just apply sort vec dot begin, vec dot end, and then we would pass comparator function here. So it will sort according to this comparator function. Now that everything is done, now we know we have a vector of pair, and inside that vector of pair we have all the pairs, and the second value of all the pairs, this is vec of 0 dot second, this is vec of 1 dot second, and so on. So we know that these values denote the structure of our tree, where the root node is this one, the first level node is this one, the second level is the third level. So what the question says is that if we have this tree, like let me write it again, so 2 3 1 4, if our tree is this 2 3 1 4, and we have all the values in the vec dot second, vec of I dot second, so we have to just print the root node, which is this one, vec of 0 dot second, and so in the first line you have to print the root node, which is 2. Then in the next lines, next n-1 lines, you have to just print the edges of this tree. So edges are these. So first edge is 2 to 3, second edge is 3 to 1, third edge is 1 to 4. So this would be our answer. I hope you understood well. If you want more solutions, then please do comment, and also do comment your doubts. So bye bye.